We talked in chapter 2 a lot about protons and neutrons because we were talking about the size of atoms, masses, identification of the subatomic particles. So remember, in the atom, the nucleus is where those protons and neutrons are. Protons being positively charged, neutrons being neutrally charged. And what characteristic do they have in common? Protons and neutrons both have what? No, well, protons are positively charged, neutrons neutrally charged. They're both in the nucleus and they both have the same mass, okay? So electrons have mass, but they're so much smaller than protons and neutrons. Relatively, you might as well say they don't have any mass. So remember that it's in the nucleus is where all of the mass of the atom is located. So this whole chapter really talks about electrons. Okay? So what do electrons do? If protons and neutrons give the atom mass, electrons are responsible for interaction between atoms. So the reason for this is that these electrons outside of the nucleus, electrons are extremely small and they're constantly moving. So in this one, you can see this, so this little red electron here, it's in this constant motion and it actually takes like a path. So it, being negatively charged, is attracted to the positive protons in the nucleus, but it's in constant motion. So it's kind of like the moon orbiting the Earth orbiting the sun. You think of electrons as sort of like having this constant motion. They're attracted to the protons, and that kind of holds them in that position. The electron that's close to the nucleus has less energy. And the way that I think about it is this one out here, the electron out here, has to make the circle at the same speed that the electron close to the nucleus makes. So which one has to move faster? The outside one. So the outside one actually has to make its loop at the same speed or the same time that the inside one does. So the inside one can go a little slower. The outside one's got to move faster in order to make the loop in the same period of time. So the further out, the further away from the nucleus, the higher the energy level. So just by all things being equal, things like to take sort of like the easiest path. The lowest energy level would be the optimal because the electron's not going to move so fast. It can have sort of a shorter path or distance. So the closest to the nucleus is the lowest energy level. As you progress further and further away, energy levels increase, the energy that those speeds that those electrons have to move increases. So lowest energy levels always get filled first. So if we just start with like the smallest of the elements, if we just look at hydrogen, remember that hydrogen has one proton and one electron. If you look at the periodic table, you see that it's 1, so 1 proton, 1 electron. If you look at the mass, you see that it's got an atomic mass of 1. So most hydrogen atoms don't have any neutrons at all, just a proton and an electron. So that electron goes in this first energy level. If you go across, helium on the all the way opposite side, over on the far right, helium with 2 protons and 2 electrons fill that first energy level. And that actually creates an atom of helium and makes it really stable. So that is actually the characteristic of that far right column, is that they are called the noble gases. They are sometimes called the inert gases. They're not very reactive and they'll exist just as elements. So they exist as individual atoms rather than forming compounds. So while you have things like H2O and CO2 and you have all of the compounds we've been talking about, helium exists as single atoms. They don't form combinations with other atoms. They're extremely stable in and of themselves. But all other elements on the periodic table, more or less, want to be like a noble gas. They want to have electron numbers like noble gases do in order to create stability. So the next energy level that the next element as we go up would be lithium. So if you go across, you've got to come all the way back to lithium, which is number 3. So lithium has 3 electrons. 2 electrons fit in that first energy level, but then the third electron has to be in the next level out. So when looking at this list, the first energy level, which is where hydrogen and helium keep their electrons completely, there's only 2 electrons that fit here. So when you have lithium, you're going to have 2 electrons in the first, and then you'll have 1 electron that goes into the second energy level. It's a little further out. Beryllium, number 4, would have its 2 electrons in the first and then 2 electrons in the second energy level. So if you look at Be, 2 electrons in the first, 2 electrons in the second. And as you continue to go across, the atomic number increases. Boron is atomic number 5. So boron would be 2 electrons in the first, 3 electrons in the second. They would continue to fill the second energy level. Carbon would have 4 in the second energy level. Nitrogen had 5 in the second energy level. Oxygen would have 6. Just as you're going across, always 2 in the first, but then the second energy level continues to fill, continues to fill. And then you get all the way over to fluorine. So fluorine, atomic number 9, fluorine has 2 electrons in the first, 7 in the second. And then you get to neon. So now neon has 2 electrons in the first and 8 in the second. And other than helium, you will find this for all of the noble gases. Their outer electron number is always going to have 8. And what they found is that 8 creates a very stable arrangement for electrons in an energy level. So they kind of balance each other. So there's like 2 on either side, 2 up and 2 down, and 2 in the front and the side. So they sort of span themselves around in that orbital. So this is an extremely stable arrangement. And that's always the goal. This led to the development of what they call the octet rule. So the word octet makes you think about the number what? Like an octagon, an octopus, right? All 8. So the octet rule is that elements want to have a total number of 8 electrons in the outer shell to create stability. So when they were starting to develop the table, knowing the elements, they started to see that as they were putting similar properties together and aligning columns, they also started to see that the outermost electron numbers were in common within the columns. So if we have hydrogen, we said how many was in hydrogen? How many electrons in the outer shell? Just 1, because that's all it's got. Right? But then look at lithium, which is right under. How many electrons in its outer energy level? 1. So hydrogen and lithium both have 1 electron in their outer shell. They have varying numbers of shell, but the outside one has 1. So sodium. So if we go to Na, Na is 11. So 2 fit in the first, 8 fit in the second, and what goes into the third? 1. So notice that hydrogen, lithium, and sodium, they all have 1 electron in their outer shell. So you actually don't have to memorize any of these. You just have to know how to use the periodic table, and it will actually tell you the number of electrons in the outer shell. So that one doesn't, which is why this one's a little bit different. Okay? If you look all the way up at the top, for the first 2 columns and the last 6 columns, which really includes elements 1 through 20, for those, at the very top of the column is a capital A. Every single one, you see all the capital A. They call these the main group elements. The number in front tells you the number of electrons in the outer shell. So like sodium has 1 electron, lithium has 1 electron, hydrogen has 1 electron. So how many electrons with potassium? 1. Everything in that column is going to have 1 electron in its outermost shell. Doesn't tell you the number of shells. You really don't have to worry about that. In this class, that's really about the most important part because it's those electrons that interact to form chemical bonds. So 2 electrons create stability, 8 electrons create stability in the second energy level. The third energy level can actually hold 18, but 8 electrons still creates this stability. Same thing for energy level 4. You have 27 out there, but 8 electrons is the stable arrangement, and that's where this octet rule came about. The only one that is really the exception is the first energy level. Because the first energy level is so small, it's so close to the nucleus, there's only room for 2. So hydrogen and helium, they are always going to just have 2. Hydrogen will never have 8 because 2 fills that energy level closest to the nucleus and creates stability. But all the other ones are always going to go on this rule of 8. So Lewis, a chemist that was studying electrons, realized that it was this outer electron. These numbers were the ones that came into play when you have interactions between atoms when you form things like H2O, or if you form things like NaCl. So he came up with what are known as Lewis dot structures. Lewis dot structures just puts the symbol, and it puts a dot around the symbol, 1 for each of the electrons in the outer shell. They name those electrons valence electrons. So the valence electron, sometimes they call it the valence number. That is just the number of electrons in the outermost shell. You really don't worry about the electrons in the inner shells because they're already stable. So like when we were looking at sodium, you don't really think about these 2 electrons or these 8 electrons because they're already stable. They're full. It's just the outside one that doesn't have its 8, and that creates the reactivity for sodium. So we can do that here. So hydrogen, and I like this one because it actually just puts, these are elements 1 through 20, and it shows the group number 1A. So hydrogen, for a Lewis dot, you would just put an H with just a single dot because hydrogen has a single electron in its outer energy level. But now knowing what you know, what do you put in front of lithium, sodium, and potassium? They too would just have 1. So group 1A has just a single dot in a Lewis dot structure because it has 1 valence electron. No matter how big it is, if it's in that first column, so rubidium, cesium, francium, all the other ones in that first column, they all have 1 electron in their outermost shell or their valence electron. So group 2, you'd put 2. 2 for beryllium, 2 for magnesium, 2 for calcium. So the ones that are in group 2A in the second column all have 2 valence electrons. So going across, skip the middle ones for right now, continuing across, find boron and aluminum. See that the number 3 at the top, that tells you the number of valence electrons. So this one, when I have more than 2, I split them. So I actually separate them, so I end up putting singles above, below, to the left or the right. So you could go this way. And I do that because that helps me to see that there's not a total number of 8. So I don't pair them automatically. So when I do carbon, it's got 4. You can tell because of that number. So you have 4 dots, and I spread them out. Silicon, same thing. Nitrogen, group 5A. Phosphorus, same. Now, you have to pair one set of them because you have a maximum will be 2 on the bottom, 2 on the top, 2 to the left, 2 to the right when you get your total of 8. And so putting just pairs on one side, above or below, left or right. So with oxygen, that means 6 of them. 2 of the dots will be paired and 2 singlets. Fluorine and chlorine, bromine and iodine, they're all in group 7, those halogens. So you end up putting 7 dots, 2 above, 2 below, 2 to the right, 1 to the left. Really doesn't matter where you put them. You just end up pairing. Pairing 3 of 3 sets, and then 1's a singlet. So it doesn't matter where the single one is, just somewhere. Helium. Helium and hydrogen are sort of the oddballs in this, because remember that helium is stable when it's just like this, because that's that first energy level. So it's really the unusual one in the noble gases, because neon and argon, krypton and xenon and radon, all the other ones have what? They all have 8, right? So that number at the top tells you the number of valence electrons. The only exception would be helium. Having that 8 is what creates stability. If an element doesn't have 8, it is reactive. It is going to try to either take electrons, give up electrons, or share electrons, and the goal is always to end up with its outer energy level having 8. So what do you notice about the metals? So the blue ones, the ones that are in blue are metals, the ones in yellow are the non-metals, and then the green are those in-betweeners. But the ones that are blue, what would you say about their electron numbers? Lots or little? Yeah, so they have few valence electrons. What do you notice about the nonmetals? The ones in yellow, comparatively, you would say that they have more valence electrons. So there's a difference between metals and nonmetals. When there's a difference between their valence number, they have a hard time sharing, because one has a strong attraction for electrons and the other one really would just rather get rid of the few it has. It would make it simpler, and in that actually causes the first example of bonding that we're going to do, and that is ionic bonding. So ionic bonding happens between a metal and a nonmetal, and it's because the metal just has a couple of valence electrons, whereas the nonmetal has many. It's close to 8, and 8 is stable. So the nonmetal is going to want to pull electrons, gain electrons with a much stronger sort of force than what the metals have. And this causes transfer of electrons. So think about sodium and chlorine from their proton and electron number. So sodium, looking at sodium, its atomic number is 11, so you know that it has 11 protons and 11 electrons. Sodium is element number 17. It has 17 protons, 17 electrons. The Lewis dot structure for this, you can see sodium has that one valence electron, just that little red dot. The chlorine has seven little dots surrounding. So can you see how chlorine almost has a full shell, whereas sodium only has one? So it would be difficult for them to share, because for sodium would have to end up getting or sharing 7 electrons from the chlorine, and that's not, you can only share if it's a one-in-one thing. You can only share if you're actually sharing a pair. So with this, you couldn't share a pair and give sodium 8. Instead, it's much easier if sodium just loses its electron, completely passes it to the chlorine, so it doesn't belong to sodium anymore. It now belongs to the chlorine. But what does that do for sodium's protons and electron number? So it still has 11 protons, but now how many electrons does it have? 10. Find element number 10. What atomic number, what element has 10 electrons? Which? Neon. By losing that electron, that is going to give it an electron configuration like neon, which is a noble gas. So it's actually going to give it a full outer shell. It gets rid of its 1, and the 8 below become the outer shell. So that's going to create, it's going to make it like neon. It's going to make it like a noble gas, and that's going to create stability for sodium. So the sodium atom then is very stable and is not going to react with anything else once it loses that outer electron. So what about the chlorine? So chlorine started with 17 and 17. It's still going to have 17 protons, but now it has 18 electrons. When you look at atomic number 18, that's what? What element is atomic number 18? Argon. So now it's like argon. C18 all the way over on the far right side. So now it's like argon. So now these two atoms but can behave like noble gases, and they're extremely stable. They form a compound because the sodium now has one more positive than negative charge. The chlorine has one more electron, one more negative charge than positive. So the sodium becomes a positively charged ion. So an ion is an atom with an unequal number of protons and electrons. So it's an atom with a charge. If it is a positive charge, it is called a cation. Cations are your metals, because cations always lose electrons. Metals always lose electrons when they form an ionic bond. If they become negatively charged, like the chlorine does, that is an anion. And that's what you see the nonmetals do. So metals lose electrons, nonmetals gain electrons when they form an ionic compound. And what do you know about oppositely charged things? What do they do? Positive and negatives are, they attract, right? Like charges repel, but opposite charges will attract, and that's what holds them together. The ionic bond is the attraction of these oppositely charged particles, and that's what forms the ionic compound. So in this, you can actually look at, name, and figure out the formula of any ionic compound as long as you know how to use the periodic table. So the periodic table is really kind of like it was in trying to figure out the numbers of protons, neutrons, and electrons. The periodic table, and you'll always have one, so you don't have to memorize it. You just have to know how to use it. So for any ionic compound, it's always going to be a metal and a nonmetal. You can always figure out how many electrons the metal will lose because that is its valence number. So the group number at the top in front of the capital A, that'll tell you the charge on any metal in the main groups. So the ones that you can think about is like Li. So when you look at lithium, lithium's in group 1, so you know that it would always end up with a +1 charge. What about calcium? What would the charge on calcium always be if it forms an ionic compound? +2, right? So it's in group 2A. So that tells you what its charge would be. So you can write +2 or you can write 2+. Either way is fine, just so long as kind of in the upper, just smaller and just above the symbol, you write the charge. So sodium would have a positive charge, magnesium a +2 charge. What about aluminum? So aluminum is a metal. What would its charge be? +3. Find it over here. It's in group 3A. That tells you the charge. So you don't have to memorize them. You just have to remember the group number at the top in front of the capital A. That tells you the charge. The nonmetals. Nonmetals are always going to gain electrons. So the nonmetals are the negatively charged part. And so the nonmetals are always up here to the right of the zigzag line. So to figure out their charge, it's how many electrons they gain to make 8. So for example, with nitrogen. Nitrogen has how many valence electrons? What group is it in? 5. So if you take 5 minus 8, that tells you -3. So that's how many electrons would it need in order to make 8. So if you take its group number minus 8, I just always think, I look at the group number and then I'm like, okay, it needs 3 in order to make 8. Like I always just figure, how many do I need to gain in order to make 8? And those are going to gain negative electrons. So it's always going to have a negative charge. So nitrogen would be a -3. That means oxygen is a -2. So what would phosphorus be? -3. Sulfur, a -2. Bromine, just a -1 because it's got 7, so it's going to gain 1 to make 8. So it's how many negative electrons would it gain to make it? That's going to tell you what the charge is. So that means chlorine would be chlorine, bromine, iodine, fluorine, all -1, all in group 7. So if I combine any metal and nonmetal, knowing the charges can allow me to figure out the formula because the total number of atoms have to balance the charges. So for example, with sodium and chlorine, NaCl, sodium is positively charged, chlorine is negatively charged. So it's like 1 and 1. Do you see that the positives and the negatives balance in this? 1 positive sodium to 1 negative chlorine. But what about Mg in Cl? What's the charge on magnesium? +2. The charge on chlorine is negative. So do you notice that those charges aren't balanced? To figure out the formula, just take the charge on the magnesium and it tells you the number of chlorine. This number goes here, tells you how many chlorine. The charge on the chlorine tells you how many magnesium. So a negative is the same as saying -1. So this will go here. The charge on the metal tells you the number of nonmetals. The charge on the nonmetal tells you the number of metals. So the formula for this would be what? 1 magnesium and 2 chlorines. The charge on the metal tells you the number of nonmetals. I just call it a swap. So you just do a swap. Assign the charge and then swap them. The only thing you have to remember is if you ended up with like 2 and 2, you want to simplify. Okay, so you would want to make it as simple as possible, then it would just be a 1-to-1 ratio. But I can't simplify this anymore. So 1 magnesium would react with 2 chlorines to make magnesium chloride. Here's another example. So if you have aluminum and oxygen, remember aluminum's group 3, so it'd be a +3. Oxygen's in group 6, so it'd be a -2 to make its 8. So if you take the charge on the aluminum, it tells you how many oxygen. The charge on the oxygen tells you how many aluminum. So see how they take that number and do the swap. So this number turns around and goes to the opposite side, and the oxygen gets turned, so it becomes the number of aluminum. So it's Al2O3. So no matter what metal or non-metal, you can use the periodic table to figure out the charges, and then all you have to do is this swap in order to figure out what the formula would be. Last thing is the naming. So when we said NaCl, what do you call that? A sodium chloride, right? That's table salt. Sodium is extremely reactive as an atom. Chlorine is very reactive as an atom, but when they react together, they make this stuff that you put on your food all the time. It's table salt. It's extremely stable. Sodium chloride, that is the rule for naming all ionic compounds. So the first element, how much of the name do you use? If you call it sodium chloride, you use the whole name of the first element. And then what do you use of the second? So that's chlorine. So we're going to call this chlor. It's like the first syllable, the first part of the second element. And then you add what at the end? IDE. So just use sodium chloride as sort of your naming rule. You're just going to follow that. So what is Al2O3? Yeah. Use the whole name of the first element. It's aluminum. For oxygen, you just use ox. So you add ox and then IDE at the end. So this is aluminum oxide. Whole name of the metal, first part of the nonmetal plus IDE. So what about this one? What would this one be down here? Magnesium chloride, right? Whole name of the metal, first part of the nonmetal plus IDE every time, okay? It seems like it should be more complicated, but it's really not. It's the same exact process. So what would you have, something that ended in nitrogen, what would it end up being? Nitride. Something that ended with oxygen, we said would be oxide. If it ends with the phosphorus, it would be phosphide. First part of the nonmetal plus IDE. If it ends with the sulfur, sulfide. Chlorine becomes the chloride. Bromine would be a bromide. Fluorine would be a fluoride. And the one that sounds really weird, but that's how you say it, iodine would be iodide. Yeah. It's the only one that people like, that just sounds strange. But iodide, it's the same one. So it's always just the first part of the nonmetal, then you add IDE to the end. They can only react in a specific ratio. When magnesium and chlorine react, they will always form magnesium chloride. They will always form MgCl2 because of the charges. So they're going to interact and transfer electrons until they have a neutral molecule. All the valence electrons from the magnesium get transferred to the chlorines, and that forms a stable compound. So what about this one? When you're looking for something and you're trying to determine if it's ionic, just look for a metal. That's really the kicker, okay? Because covalent molecules don't have metals. So if you see a metal, and remember that you can identify a metal, you don't have to memorize that either. Metals are always on the left of the zigzag line, right? So if you see a metal, you know it's ionic. If there are no metals, 99.9% of the time it's covalent, okay? Almost always, and I'll tell you about the one exception, but almost always, just look for the metal. So compare the elements in the molecule name, compare them with the periodic table. If you see an element to the left of the zigzag line, then you're going to call it a metal, and it's ionic. When you go to write it, you always list the metal first, okay? So even though if I say, okay, what if you mix bromine and calcium together, okay? So you look at the two and you're like, well, calcium's a metal. Calcium gets written first. The metal always gets written first. then the nonmetal. So I'm going to mix calcium and bromine. So I'm going to have transfer of electrons. What will the charge be on calcium? +2. Because it's in group 2. So the charge on calcium will be a +2. The charge on bromine? 7. It's a group 7. So what does that mean? It'll be a -1. Because remember, with the nonmetals, it's how many it gains to make 8. So you can think, if it's group 7, 7 minus 8 gives you the -1. So now, how do I figure out the formula? Just flip them. Just do the swap. The charge on the metal tells you the number of the nonmetals and vice versa. So the formula would be Ca Br2. So remember that this is like a 1. So 1 calcium, 2 bromines. The charge tells you the number of each in the formula. And then what's its name? Yep, calcium bromide. I don't have to simplify. I'll give you an example of a simplify. I think it's in the next one. Yeah. So let's do these 3 right here. So MgO, magnesium is +2, oxygen is -2. So in this one, if I was trying to figure out the formula, I would do the swap and I would end up with Mg2O2. But in that one, the simplest ratio. So when you look at this formula, the simplest ratio would just be what? Just MgO. Because I can cancel them. I divide both by 2, so I could simplify it. And then what's its name? Magnesium oxide. The name of the next one is just calcium chloride. Whole name of the metal, first part of the nonmetal, add the IDE. K3N, its formula is because the nitrogen's a -3, the potassiums are a +1. So see how you swap to figure out that ratio? The number on the nitrogen tells you how many potassium. The charge on the potassium tells you how many nitrogen. So that's where you get the K3N. And its name? Potassium nitride. Just follow the steps with each one. So I'll make sure everybody's got them. So this one's an additional slide. So these are just for you to practice. So in the first 4, tell me the name. In the second 4, tell me the formula. Okay, so in the first 4, from the name, I want you to give me from the formula, I want you to give me the name of it. In the second 4, starting with the name, tell me what the formula would be. Okay, so what did you get for the first one? Magnesium chloride. Anybody not? Okay, what about the second one? Potassium sulfide. I did these ones specifically because they use all the nonmetals to make you go over the names to try and help get used to some of the pronunciations. BeF2. What is Be? Beryllium fluoride. Beryllium fluoride. Okay, and when you do beryllium, remember fluorine is Fluor, because if you put an OUR, it's flour. Okay, so it's beryllium fluoride. And then the last one, lithium phosphide. Great. And with the other ones, you first have to list the element, assign the charge, and then do the swap. So what is sodium? Na, and charge plus. Bromine is Br, and charge negative. So when you swap, it's a 1-to-1 ratio, doesn't change anything, so it's just NaBr. Calcium is +2. Oxygen is -2. So again, here I swap. So that would give me Ca2O2. But the rule is to simplify, so you would just put CaO. Aluminum nitride, Al, will be the charge. +3. See, it's in group 3A, so it's a +3. And then nitride is nitrogen, and it's a -3. Because it's in group 5, so it needs to gain 3 to have 8. So if you swap this one, it would be Al3N3. But you've got to simplify, so it would end up being a ALN. 1-to-1. So just make sure that you go back, simplify them if you can. So then the last one, magnesium iodide. Magnesium is Mg+2. It's in group 2A. Iodide is an I, and it's negative. So when you swap this, what's the formula? Mgi2. Okay, not terrible, not as hard as maybe you thought. Okay, it's just following that same pattern. There's a lot of this. You'll see to follow this pattern. Practicing it really helps, and in that way, that chemistry has a lot of like similarities to math, and that practicing it, suddenly you just start, you're seeing it easier because you do it over and over and over again. You create the little brain memory in there. So there's 2 oddballs. Sorry. There's always something, okay? There's 2 oddities. The first one are these. I like this chart. This chart splits those main groups, tells you the charges, helps you to review. Remember, everything in group 1 is a plus, group 2 is a +2. Going over, aluminum's a +3. All those nonmetals have their negatives, so this is a good chart just to review what the charge would be for normal ionic compounds. But then there's these oddballs in the middle. So this group here, they call them transition metals. They called them that because they found that they have the ability to lose varying numbers of electrons and become stable. It all has to do with the size of their atom and the number of electrons in the valence shell. So they found with Cr, so what's Cr stand for? There was one on your test even. Chromium. So chromium Fe is iron. Cu is copper. So those are the 3 that I want you to be familiar with. They found that chromium, iron, and copper are 3 that have the ability to either lose 2 electrons or lose 3 electrons. Copper can lose 1 electron or lose 2 electrons and create stability. So they have the ability to exist and make more than one type of ionic compound with a nonmetal. So for example, you can have this, CrCl2, or you could have CrCl3. So when you look at each of those, what do you want to name those? You would say, well, that's chromium chloride, right? Like based on what we've been doing all along, you would just want to call that chromium chloride. But how would you tell them apart? So if you just called them chromium chloride, you'd be like, well, it depends on what the charge is. So in this, they went to a Roman numeral system that they add to the name that indicates the charge. So what we want to indicate is we want to know what the charge on the chlorine is. But you can figure it out. What's the charge on the chlorines? Every chlorine always has a negative charge, right? See over here, chlorine's got a negative charge. And that you're sure of. And so it's kind of doing a reverse swap. Okay? So chromium's got a 1 and chlorine's got a -1 charge. So you see where that is. And so what does that mean? What's the chromium's charge on the top one? It would be a positive what? Do the reverse swap. So the formula will tell you the charge. So this will be a +2. Okay, so remember we assigned charges and we could figure out the formula. So with these, you can look at the formula and actually figure out what the charge would be. So they swap backwards. So that 2 here tells you the charge on the chromium. So that's a +2 chromium. What's the other one? So this is going to be the +3. So the number of chlorines is going to help you to figure out what the charge on the chromium would be. So yes, we would still call both of these chromium chloride. It would both be that. That is their correct name. But we're going to add a Roman numeral which tells you the charge on the chlorine. So the first one would be 2. The second one would be 3.
Does the number of chlorine cancel out?
It's not that it cancels out. So remember when we did this, remember when we did like magnesium oxide. So magnesium's plus charge, oxygen's minus. So we took this and did the swap to figure out the formula. So in this one, really all you're doing is you're just going backwards. So you're taking the number here to figure out the charge. We're taking the number on the chlorine to figure out the charge on the chromium. Sort of like a reverse swap. So you're using the formula to figure out what the charges would be. So let's do a couple other ones. So with iron, so what if we have FeO and Fe2O3? So both of those, what would their just generic name be? They'd be iron oxide, right? Whole name of the metal, first part of the nonmetal plus the IDE. So they would both be iron oxide, iron oxide. But because they're one of these transition metals, you've got to figure out what the charge on each is. So what's the charge on an oxygen? It's -2. So you can see that over here because it's in group 6. So it would have a -2 charge. So that's a -2 and this one's a -2. So if the oxygen's a -2, what would the iron have to be in the first one? The charges have to balance. A +2. So you see if oxygen's a -2, iron's going to be a +2 because there's only one of each. So they would balance, sort of like how magnesium oxide is. They would balance each other. The total number of charges are balanced between the two. So this one would be iron 2 oxide. Roman numeral 2 tells you there's a +2 on the charge for the iron. Second one, the iron's -2 and there's 3 of them. So what's the charge on the iron? This is a plus. It's a +3. The charge on the iron is a +3. And this one's a good example where the formula swapped backwards tells you what the charges are. You could also think like the total number of charges. I have 3 oxygens each of them has a -2 charge. So if I have 3 of them, what's the charge over on this side? This is really like a -6. So I have 3 oxygens, each with a -2. So -2, -2, and -2. I've got a total of -6. And so on the opposite side with the iron, I have 2 of them. I have to have a +6. So that means each of them would be the +3. So the total charges per atom on each side have to balance each other out. But it's a good example of what I would call like that reverse swap. The formula tells you the charge on them. So the Roman numeral here would be a Roman numeral 3. So let's look at copper. So if I have CuS and Cu2s. So just its generic name would be copper sulfide. Copper sulfide. First whole name of the metal, first part of the non-metal plus IDE. But because it's one of these 3, and these are the only 3 that you need to know, so, or need to really remember, we're going to talk about iron again. We're going to talk about copper again. So we will actually talk about them and their charges again. It's a reason to put these ones down, and I'll just let the other ones go. But there's some other examples up there, but just these 3. So in the first one, what's the charge on the sulfur? It's a -2. So that means the charge on the copper has to balance it, so the charge would be +2. So the Roman numeral after the word copper, you put the Roman numeral 2. The charge is that Roman numeral. It doesn't mean you have 2 coppers, because I've had some students think, well, copper 2 sulfide means it's a copper and there's 2 of them. No. The Roman numeral tells you the charge, and that can help you to figure out the formula. So what about the second one? Still -2. Sulfur doesn't change. It's going to be a -2, but I have 2 coppers. So that means each copper has a charge of +1. So if the sulfur has a -2 and there's 1, then the 2 coppers together have to balance it with a positive charge. So there's 2 of them. So that one, see how the reverse swap? The number of copper tells you the charge on the sulfur. The number of sulfur tells you the charge on the copper. The top one's a reverse swap. It's just the fact that it was simplified. That's why it's not a 1-to-1. So as long as you assign, first thing to do is assign the charge to the nonmetal. Okay? And then you can compare. So then you can assign the charge and compare to see, does the charge on the nonmetal equal the formula for the metal? If it's that, then you can just reverse swap. If it's not, it's probably because it was simplified. So you have to make sure the total number of positive charges, total number of negative charges are balanced. So the Roman numeral here would just be a 1. So that's copper 1 sulfide. This is a whole lot easier. They used to use cupric and cuprous, which are like Latin forms, but they finally stopped. So they went back to like a common naming. So they just use the name of the metal, but the Roman numeral tells you that charge. All right, we got time for the last one. I told you there's 2 oddballs. We got all that. Here's the oddball. Second oddballs. Polyatomics. Now for this next exam, you will still get a card, okay? So maybe these ones, the polyatomics, maybe the copper, chromium, and iron naming, maybe you want to start making a list. So I told the night class, I said, you should start like a separate list of stuff I want to put on this note card. Start it now, okay? And if you kind of are going through things with each lecture, put down things that you think, I might want to put that on the note card. Because it's hard when you get to the night before the test and you're trying to do your note card and you're like, I don't even remember what we were talking about back then. Okay, so these you can start writing notes, start writing a list. What do you want to put on a note card this time? Okay, you'll see, I'll give you back the exams in a couple minutes. You'll see the The ones you'll have time to look at it, figure out what you did right, figure out what you did wrong, so that you can make sure that you adjust your studying or you adjust like your note card. I should have put more information about that down, but do start kind of keeping this in the back of your mind already. Like start writing things that you think will fit that you might want to add for this next one. Polyatomic ions, these are groups of nonmetals that have a charge. Nonmetals that have a charge. They are typically nonmetals with a bunch of oxygens. There are 7 that you need to know: the name, the formula, and their charge. So these 7, almost undoubtedly, you're going to want to write on your note card. They're the ones I have in boxes, and there's only 2 other boxes to add. So the most common forms are listed on the boxes. And then I've got those other 2 at the top because we're going to talk about hydroxides. Hydroxides are characteristics of bases. When we talk about acids and bases, we're going to talk about the hydroxides over and over and over again. So understanding and remembering, picking up that OH is a hydroxide is going to be helpful. So hydroxide, OH. When you name polyatomics, you just use the name of the polyatomic. So when you see OH, you're not going to call it like oxygen hydride or anything like that. You're just going to call this one the hydroxide. So if I have NaOH, we actually use this in lab. This is what you put on your piece of egg and it got all mushy. Okay, I told you it was kind of like lye or Drano in terms of its strength, and its name is what? Sodium hydroxide. So the OH, you just use the name of the polyatomic and it's like a group there. So this one, sodium hydroxide. I'm going to skip the NH4 one for now because we're just going to talk about the negative ones first. So the next one is a nitrogen with 3 oxygens. It is an NO3. It is a nitrate. If it was just a, wow, nitrate. It's because I was just about to say if it was just an N, it'd be nitrite. So then I just wrote IDE at the end on there. No. So, and if you see an NO3, that is a nitrate. So the name of this one would be KNO3. K is potassium. So you would call this potassium nitrate. So you just use the name. You just use the name of the polyatomic. You don't have to like break the nitrogens and oxygens down. The NO3 as a group is a nitrate ion. ClO3 minus, that is the chlorate. A chlorine with excess numbers of oxygens. A chlorine with 3 oxygens, totally it has a negative charge. Notice it's got a negative charge, so if I put it with magnesium that has a +2 charge, it will have to have parentheses. So 1 chlorate is a negative, so with make a formula with a +2 metal, it would end up having to do swapping of the charge. Remember you saw that in balancing equations? If you go back and look at your balancing equation worksheets, they're all going to be sulfates, chlorates, nitrates, hydroxides, all the things that end up having parentheses with the number out, and you had to make sure that you added that multiplied by the number outside. Those are grouped together that way because they're all polyatomic ions. So that one you would call what? Magnesium chlorate. You don't have to use any numbers or anything else. It's the whole name of the metal and just use the name of the polyatomic. Okay? So magnesium chlorate, CO3. This is a 2-. This is the carbonate. So if I have CaCO3, calcium's a +2, carbonate's a -2. They're just a 1-to-1 ratio, and you would call that calcium carbonate, CaCO3. Sulfate, also a -2, SO4 -2, that is the sulfate. sulfur with 4 oxygens. So in this one, if I had Na2SO4, I would have to have 2 sulfurs. Notice that the sulfate is a -2 charge. So I'd have to have a 2 with the sodium. This is the plus, this one's a -2. So we'd be swapping to figure out the formula. And the name for that one? Sodium sulfate. And then the last one we'll do. Last one is PO4. It's a 3-. So this is a phosphate. This is one of the components that you find in the backbones of DNA and RNA. You have sugars and phosphates. So this is the phosphate group. A lot of oxygens on this one, a phosphorus with 4 oxygens and a -3 charge. So I would have K3PO4. I'd have to have 3 potassiums. Remember, potassium's a +1. Phosphate's a -3, so you'd have to do the swap with that to figure out the formula. And the name for that would be potassium phosphate. Always just use the name of the polyatomic. So you don't have to split the phosphorus and the oxygens up. You call a PO4 a phosphate. So make that this list. We will talk more about, I'm going to talk about the ammonium when we come back on Tuesday. We'll talk about that one. We'll do some practicing of making names and formulas. It really follows the same rules that we've done with ionic, and then we're going to go on to covalent. Okay, so